We've all seen maps that look something like this, where they've got states or countries even, and they're colored in different colors. And usually the way it works is if you see a state or a country that's green, nothing directly around it or bordering it would also be green. And so you've got a pink one here, shouldn't be bordered by another pink one. And at some point, somebody had to figure out how to do that. How many colors do I need? What's the least number? If it was just black and white, that's kind of a hard question, because you can start coloring and color this one green, and you can say, well, can I color this one green? Or I don't know which colors, but whoever solved this problem, they solved it using graph theory. So what you can do is make a graph out of whatever map you're looking at, and each country or state would be a vertex, and you would show the border with an edge. So this edge represents these two countries touching each other. So we're going to use graph theory and an idea called graph coloring to figure out how they answered that question. A subgraph is a graph consisting of some of the vertices and edges of the original graph. So it's just a piece or a part of the original graph. Coloring is what we want to answer the map question. How many colors do I need? What's the least number of colors I would need to color a map? Step 1, choose a vertex with greatest degree and color it. That should probably be inside quotes, because we're not really coloring when we're doing graph theory. Use the same color to color as many vertices as you can without coloring two vertices the same color if they're joined by an edge. So what that's saying is you don't want to color two states the same color if they're right next to each other. Step 2, choose a new color and repeat step 1 for vertices not already colored. Repeat step 1 until all vertices are colored. What we're trying to find is called the chromatic number. The chromatic number is the least number of colors needed to do what we're talking about, to make a coloring. We are not literally coloring. We're trying to find the least number of colors or groups. 11. Study groups must be scheduled at different times if there are students taking both courses. Help find the most efficient way to schedule study groups by finding the least number of time slots necessary to schedule all courses without conflict. So I've got 1, 2, 3, 4, 5, 6, 7 vertices on my graph. So let's start with that. Algebra and history, chemistry, biology, physics, statistics, and writing. And it doesn't matter what shape you make, just kind of spread them out. I'm going to show the connections. Algebra goes to statistics, chemistry, history, and physics. History goes to statistics, chemistry, biology, and algebra, which I've already got. Chemistry goes to physics, biology, writing, algebra, which I've got, and history, which I've got. Biology goes to physics, statistics, writing, history, I've got it, and chemistry, I've got it. Now we do physics. Physics goes to statistics and algebra, which I've got, and chemistry, which I've got, and biology, which I've got. Now we do statistics. Statistics goes to writing, algebra, got it, history, got it, biology, got it, physics, got it. And then writing goes to chemistry, got it. Biology, got it. Statistics, got it. All right, there's my graph. Now I'm going to color this graph. Now, coloring does not literally mean coloring, so please don't literally color. We're going to follow these steps. Choose a vertex with greatest degree. So let's look at the degrees of the vertices. Degree 3, degree 4. Degree 4, 1, 2, 3, 4, 5, 5, 4, 5. So we've got several different vertices with a degree 5. So really you just kind of pick one. Pick one. You're picking something with a lot of connections. So I'm going to, what does it say? It says, choose a vertex with greatest degree and color it, quote unquote. Use the same color to color as many vertices as you can without coloring two vertices the same color if they're joined by an edge. So what we do, okay, I'm going to call this one color 1. And I look for things basically that aren't connected, okay? So you wouldn't color any one of the vertices that are attached to color 1. So that pretty much leaves algebra. So I'm going to color, quote unquote, algebra. I could color, if this was a map, I could color those two things the same color. This is not a map, so we're doing something else. We're talking about time slots. We're talking about scheduling, but it's the same exact concept. All right, so you look around and see if there's anything else that doesn't touch either one of those color 1s. And it looks like everything else either touches one or the other. So what I'm going to have to do is move to a new color. So I'm still starting with the highest degree. So I see a degree 5 over here. Let's color this degree 5. Color 2. And it doesn't matter that I'm choosing the color blue, just whatever it is, category 2 if you want. And I look for things that aren't touching that color. So nope, 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 nope. Pretty much just leaves chemistry. Chemistry is going to be that same color. And you look around and see if there's anything else that doesn't touch either one of the color 2s. And everything touches one or the other. So we need a new color, a new group, a new category. And so pick the highest degree. And I see a degree 4. Doesn't matter which one, pick one. And I'm going to call that color 3. And you look around for anything that doesn't touch. I would try to stick with my highest degrees, I guess. And this history over here does not touch that color. So I would color that the same color, the same category. And you keep going because you look around and see if there's anything that doesn't touch either one of the green ones. And there is. This one doesn't touch either one of those green ones. And so I can color that the same color. The goal is to use the least amount of colors or the least amount of groups or categories possible. And so it looks like I've got 3 categories, 3 colors. Now remember, the chromatic number is the least number of colors needed to make a coloring. I needed 3 colors here, so my chromatic number is 3. If I was making a map, I would need 3 colors. I'm not making a map. I'm trying to schedule study groups. And so I need 3 time slots, 3 groups. That's what that chromatic number of 3 tells me. So time 1. So if we're scheduling, maybe we say Monday at 6 p.m. That's our first study group. And in that first study group, we can have the color 1, which were algebra and biology. These 2. time 2 looks like statistics and chemistry. And then we needed a time 3 or a color 3. Oops, let's make that black. And that was physics and writing. I don't know how to abbreviate these. And history. So keep in mind what the end goal was. We were trying to find the most efficient way to schedule these study groups. We've got 7 different courses, but we didn't need 7 different time slots. We're not going to do, every day of the week at 7 p.m. We figured to be efficient, we would only need to schedule 3 time slots. And so graph coloring and graph theory helps us solve a practical, real-world problem.